The flash over Russia came without warning. One moment, the residents of Chelyabinsk were going about their ordinary Friday morning routines, sipping coffee, driving to work, scrolling through their phones. The next moment, the sky exploded with light brighter than the sun. Some people felt the air temperature spike. Those who looked up saw a fireball streaking across the heavens, trailing smoke and fire. Then, 23 kilometers above the city, the building-sized rock detonated with the force of 30 Hiroshima bombs. 90 seconds later, the shockwave arrived, shattering windows across 6 cities, injuring over 1,500 people and sending a ripple of terror through millions. The date was February 15, 2013, and the terrifying truth was this: nobody saw it coming. Not one telescope on Earth had detected this cosmic bullet before it slammed into our atmosphere at 67,000 kilometers per hour. Within 4 days, debris from the explosion had circled our entire planet. And here's what keeps astronomers awake at night. That rock was small. Imagine if it had been bigger. Right now, somewhere in the darkness beyond Mars, rocks the size of mountains are silently drifting through space. Some are tumbling end over end. Others are spinning like tops. They're made of iron, nickel, ice, and stone, compressed over billions of years into cosmic cannonballs. And some of them, we don't know how many, are on paths that intersect with ours. Earth isn't sitting still in space. We're hurtling around the sun at 107,000 kilometers per hour. We're playing the highest stakes game of dodgeball imaginable, except we can't dodge. Our only hope is to spot the incoming threats early enough to do something about them, and that means someone needs to be watching. Someone needs to stay up all night, every night, hunting for the rocks that could end civilization. That's exactly what happens at places like the Catalina Sky Survey in Arizona, where astronomers conduct a nightly vigil while the rest of us sleep. Their telescope sweeps across the sky in a methodical grid, photographing each section 4 times in quick succession. The magic happens when you compare those 4 images. Stars stay in the same position, but asteroids move. A new point of light that shifts slightly between frames might be a harbinger of doom, or it might be nothing. A satellite, a cosmic ray hitting the detector, or any number of false alarms. The astronomer's job is to sort the real threats from the noise, hitting no hundreds of times per night until, maybe, they find something that makes their heart skip. A genuine, previously unknown asteroid. And if they find one, they get to name it. But more importantly, they've just added one more data point to humanity's cosmic defense system. Since the 1990s, ground-based observatories around the world have cataloged over 39,000 near-Earth asteroids. That sounds impressive until you realize we're probably missing hundreds of thousands more. Think of space near Earth as a shooting gallery where the targets are invisible, moving at different speeds in different directions, and some of them have our name on them. The asteroids we worry about come in 3 terrifying categories. First, there are the city killers. Rocks between 50 and a few hundred meters across. On June 30th, 1908, one of these grazed our atmosphere over Siberia and never even touched the ground. The shock wave alone flattened 80 million trees across 2,000 square kilometers. If that had happened over a populated area, millions would have died. An asteroid this size releases energy equivalent to hundreds of nuclear bombs. We think there are hundreds of thousands of these objects near us, and we've only found a fraction of them. Then come the country killers, asteroids several hundred meters to about a kilometer wide. One of these would devastate an entire nation, trigger tsunamis across oceans, and throw enough debris into the atmosphere to disrupt global agriculture for years. We've identified maybe half of these. The rest are out there, unseen. And finally, the extinction-level asteroids, rocks a kilometer wide or larger. The one that killed the dinosaurs was roughly 10 kilometers across, wider than Mount Everest is tall. When it struck what is now Mexico's Yucatan Peninsula, it released energy equivalent to billions of nuclear weapons. The impact created mega tsunamis taller than skyscrapers, a thermal pulse that ignited forests across continents, and ejected so much debris that the sun was blocked for over a decade. 75% of all species on Earth vanished. But here's something that should terrify you. That wasn't even the largest asteroid to ever hit our planet. About 1.8 billion years ago, a rock nearly 15 kilometers wide crashed into what is now Canada. And 170 million years before that, an asteroid 20 kilometers across, so large that if you'd looked up it would have filled half the sky, slammed into South Africa. Some scientists theorize that an object the size of Mars collided with Earth 4.5 billion years ago, and the debris from that cataclysmic impact eventually coalesced into our moon. The good news is that we've found most of the really big ones. Astronomers estimate we've cataloged 95 to 98% of asteroids a kilometer wide or larger, exactly 877 of them as of now. Scientists track their orbits with obsessive precision, and none are currently on a collision course with Earth. But for the country killers, we've only found about 42 to 47%. And for the city killers, the number drops precipitously. This is the gaping hole in Earth's defenses. Somewhere out there, rocks capable of obliterating entire metropolitan areas are silently approaching, and we have no idea they exist. This is what keeps the asteroid hunters working through the night, eyes burning from screen fatigue, drinking bad coffee, and scanning image after image, knowing that the next one might reveal something. That changes everything. When an observer at Catalina Sky Survey spots something suspicious, the protocol is immediate and exacting. They report their finding to the Minor Planet Center, which checks whether anyone else has already cataloged this object. If it's genuinely new, telescopes around the world lock onto its position within hours, building out its orbital path for weeks, months, and years ahead. This is a global effort. The data is public. Anyone with a telescope can contribute, and we would all need to help if something big enough were discovered. The turnaround time is critical because those 4 initial images only capture a tiny fragment of the asteroid's trajectory. Wait until morning to process the data and you might lose it forever. An undiscovered asteroid is bad. A discovered and then lost asteroid is arguably worse, because somewhere in the back of your mind, you know it's out there. So what happens if we actually find one headed our way? In 2013, the United Nations created 2 groups for exactly this scenario. One gathers information from astronomers worldwide and shares it with governments. The other brings space agencies together to formulate a response plan. Your options are surprisingly limited. You could do nothing and hope it misses, not a strategy anyone would actually choose. Or you could try to change its path just enough to turn a direct hit into a near miss. This might sound like science fiction, but we've already tested it. In 2022, NASA's DART mission deliberately crashed a vending machine-sized spacecraft into an asteroid at 22,000 kilometers per hour. The goal was to alter the asteroid's orbit by 73 seconds. Instead, the impact changed it by 32 minutes, 25 times more effective than predicted. The success was staggering. There are already blueprints for larger versions, like Hammer, a modular spacecraft that could stack together like massive Legos, creating an enormous battering ram designed specifically for planetary defense. Then there's the nuclear option, though not in the way Hollywood depicts. You wouldn't nuke an asteroid to blow it to smithereens. That might create dangerous fragments that gravity would pull back together anyway. Instead, the idea is to detonate a nuclear device just off the asteroid's surface, vaporizing one side and turning the entire rock into a rocket. The expanding gas would push the asteroid onto a new trajectory. We see this naturally with comets, whose jets of vapor push them into unexpected paths as they approach the sun. But we've never tried it with an asteroid. Other proposed methods venture into increasingly speculative territory. ion beam deflectors that shoot charged particles at the asteroid, cosmic bullets made of tungsten rods placed in the asteroid's path, or gravity tractors. Massive spacecraft that attempt to tow asteroids using gravitational attraction. The key to all these methods is time. You need years, ideally a decade or more, between detection and impact. A tiny nudge early on translates to a massive miss later because space is so vast. Change an asteroid's velocity by just a few millimeters per second 6 years before impact, and it arrives at the collision point hours before or after Earth passes through. That's why the asteroid hunters keep scanning. That's why they stay up all night, eyes glazed, clicking through image after image. Because the earlier we find a threat, the better our chances of survival. We are the only species in Earth's history capable of defending our planet from cosmic threats. Every other organism that has ever lived, from the smallest bacterium to the mightiest dinosaur, was helpless in the face of asteroids. We are not. And that makes us responsible not just for ourselves, but for all life on Earth. So if you believe that there should be more optimistic science and tech stories, subscribe to support the show. And if surviving an asteroid wasn't enough, go watch more thrilling science-backed documentaries. See you in the next.